Hello everyone, and welcome to this joint event between ANCOLD and the Queensland Tailings Group. ANCOLD has been trying to strengthen relationships within similar organizations, and this event goes in that line. Today we will cover two related topics. First, David Williams will present about lessons learned from tailings dam breaches, and then Brett Stevens will give us an update on ANCOLD guidelines on tailings dams. Even though we cannot eliminate the risk of breach of a tailings storage facility, it's very important for us to learn from what happened in the past so we can prevent similar failures in the future. And guidelines are those that set the minimum requisites, the minimum requirements for us to manage risk properly. I will start with a disclaimer that it's basically about what is the intention of this event and what presenters are going to mention about it. This event aims to fulfill ANCOLD's mission of sharing knowledge. However, the opinions expressed by the presenters are their own and are not necessarily endorsed by ANCOLD. I would also like to mention just a few things about housekeeping in general. Each presentation will be followed by questions and answers, and you are welcome to write questions as they are raised, as they arise. And at the upper right-hand corner of the screen, you will find these two buttons. On the left-hand side, you can see the chat option that must be used for general comments, and please use the questions and answers button only for questions directed to presenters. And if we have enough time and we are not able to answer all the questions after each presenter's presentation, we'll answer more questions at the end of the event. I would now like to introduce David, who initiated and directs the Geotechnical Engineering Centre and manages the industry-funded Large Open Pit project at the University of Queensland in Brisbane, Australia. He has over 40 years of teaching, research and consulting experience. He is internationally recognized for his expertise and experience in mine waste management and mine closure, particularly tailings. He also researches numerous topics in civil geotechnical engineering. David was on the expert panel that investigated the technical causes of the Brumadinho tailings dam failure in 2019 and chairs a number of tailings ITRBs internationally. David initiated in 2020 and largely delivers the highly successful ANCOLD Professional Certificate in Tailings Management. Over to you, David.
Just have to find the right presentation. Screen. Why can't I find it? There we go. So you should now see my presentation coming up.
Yes, we can see it.
And I'll just put it in presentation mode. I'm trying to. Here we go. Perfect. Okay, so welcome to this presentation, and hopefully I'll pass on some useful pointers on lessons from tailings dam failures. Firstly, I'll make the point that tailings behaviour is very complex. Some might say even intractable. When I asked Dr. Idris in 2018, what would you do with liquefiable tailings? He said, I'd avoid them. You wouldn't build a water dam using liquefiable materials or sitting on a liquefiable foundation. Why would we do it for tailings dams? And yet, sometimes we do. That's not to say that upstream construction cannot be made to work, but there are certain lessons or rules that we have to follow. Dr. Morgenstern has often said that if tailings are susceptible to liquefaction, assume that they will, at some stage, which could be during operations or it could be post-closure, which is essentially in perpetuity. The next question is, what is their post-liquefaction strength? Fundão and Brumadinho both tell us that on flow liquefaction, the strength is measured in pascals, not 20% of the peak. So 20% of the peak might initiate failure, a liquefaction type failure, but once they flow, their strength is virtually zero. Tailings dams can only be taken to limited height upstream to avoid loose and wet tailings at depth, and also only to limited height on soil foundations. And these are two of the key lessons that we've learned from recent failures. Marginal stability of slurry tailings facilities. Tailings dams that fail have marginal stability. Stable dams should not fail. Perhaps 1 in 100 tailings dams that have marginal stability fail, but of course not all of them do. Failures at El Cobre, Mount Poly, Fundão, Cadia and Brumadinho have focused our attention. The ongoing failure rate and severity is unacceptable by anyone's measure. Let's think about what were the inferred pre-failure factors of safety for these four failures, just discounting El Cobre for a moment. Mount Poly. It was believed that the factor of safety was 1.43 for a design that included a 2-to-1 downstream buttress slope. The back calculated value was about 1.1 because what they actually built was a 1.3-to-1 or angle of repose slope, and they had, of course, a weak foundation. So it was nowhere near the 1.43 that they thought they might achieve. Fundão had a peak drain factor of safety of somewhere between 1.6 and 2.0. You won't find that in the expert panel report. There's no mention of it. There was no undrain or post-seismic factor of safety calculated at the time. Of course, it failed, so the factor of safety was actually about 1. Cadia, the presumed factor of safety, was greater than 1.5. That calculated around about 1.15 for construction, the constructed geometry, and also for the weak foundation that was unknown. Brumadinho, the calculated peak undrained factor of safety, which was required by that time after the Fundão failure, was 1.09. The actual failure factor of safety is 1. This is the only factor of safety we know with certainty. All the others are just calculated. Let's think also about the setting of the site, the climate, the topography, the seismicity. All of these persist. They're there before the tailings dam, they're there during operations, and they persist post-closure. Think of Australia, and I've highlighted in green the things that are favourable in terms of climate, topography, and seismicity in terms of stable tailings dams. We're semi-arid, we're flat, we have low seismicity. You might say Australia is the ideal climate for a tailings dam to be constructed. If we look to Brazil, here I've highlighted in red the things that are a little anti-stability. So Brazil, it's generally wet. It's also steep, but it has low seismicity. Steep meaning that you can end up with quite high dams, much higher than you get in Australia. And then, of course, Chile, arid to semi-arid, that's a positive. Steep terrain, we're in the Andes quite often, and high seismicity. So high seismicity is the key to safe design in Chile, but the fact that it's steep means you end up with high dams. So don't forget about the climate, the topography, the seismicity. Sometimes we do. Let's think of El Cobre, March 1965, a seismic liquefaction failure. And there were changes for good that came out of this fatal El Cobre tailings dam failure. If you look at it before and after, the pre-1965 El Cobre tailings dam, before and after, the black is the before, the after is the red. A couple of things you pick up. In the black, you can see there's a setback, a very common way of supposedly increasing stability by stepping back your embankment. Doesn't always actually help. And the red is the post-failure shape. And notice the number of scarps. So it's a series of progressive back scarps that go back up through the facility. The number of fatalities, somewhere between 200 and 350. It wasn't a particularly high dam, but it went through the town of El Cobre. The reason why they don't know the precise number is they didn't know exactly how many people were there. And of course, they didn't have DNA in those days, so they couldn't accurately tell how many body parts they'd actually discovered. Now, the outcome of El Cobre was that the downstream slope was halved, so essentially doubling stability, and they ceased upstream raising. Downstream and centerline construction of sand and earth dams persisted. Upstream geomembranes and central cyclone stations were installed. The upstream geomembrane was to try and limit the amount of water that came from the slimes into the sand dam, and the central cyclone stations meant that you had a more uniform supply of sand to build the dam. And that's what it looked like. And I've compared there the red with the green. You can see the enormity of the embankment, the stable trapezoid of support, if you like, post-1965 compared with what was done pre-1965. It's a good story. If we look at the performance of Chilean sand tailings dams since 1965, this is after Luis Valenzuela, the total number is about 740. Active dams about 100, mostly they're downstream sand dams built in the way that I just described. Inactive tailings dams about 470, mostly upstream sand dams, and you've got abandoned dams about 170, also mostly upstream sand dams. Active Chilean downstream sand dams have performed well since 1965 due to the improved construction methods, which were induced not so much by the regulators, it was induced by the industry. The regulations took another 5 years to come into effect. With the exception of a few inactive upstream sand dams in central Chile, most inactive and abandoned upstream sand dams have performed well since 1965. Because, of course, they're not being used anymore and they've drained down in the dry Chilean climate. Let's look at Mount Polly, August 2014, a foundation failure. This is what it looked like. Unfortunately, there was water and slimes against the dam at this location. Perfectly chosen, you might say Murphy's Law. If there'd not been water and slimes against this part of the embankment that failed, you may not have had the overtopping and you may not have had the erosion of the dam and the spill of the amount of tailings that came out. Looking at the expert panel investigation and review 2015, they asked a number of questions. What was the technical cause of the failure? And essentially it was this weak foundation layer that was pre-consolidated prior to loading, but was loaded up to the point where it became normally consolidated. That would make it much less stiff, about a factor of 10 less stiff, and hence it would deform much more as the loading was increased. The failure was triggered by the construction of a downstream rockfill zone at an angle of opposed slope when it was supposed to be 2:1. It is noted that tailings, water and slimes were against the embankment, as I said, at the location of the failure, leading to overtopping and erosion and the run out of water and tailings. They also asked what would mitigate the risk of future failures, and they were asked to do this specifically in this particular project. And they said improved adoption of best applicable practices, BAP, and migration to best available technology, or BAT. Examples of BAP are improved corporate design responsibilities and the adoption of independent tailings review boards. Examples of best available technology are filtered, unsaturated, compacted tailings, and reduction in the use of water covers for closure, which are quite a feature of Canada because of their wetter climate. Let's turn now to Fundão, November 2015, a flow liquefaction failure. It failed in seconds. It liquefied in seconds, killing 19 people. Fundão is to the right. I don't know if you can see my pointer over here. This is the Germano Dam, much more stable, which was essentially still intact. There were dikes between the two, which fortunately didn't fail, because if they had, the much larger Germano Dam may have spilled through the Fundão failure and created a much worse end result. This is what it looked like downstream. And this progressed all the way to the coast with suspended solids travelling about 600 kilometres all the way to the coast on the other side of the country. Again, turning to the expert panel report in 2016, questions were asked, why did a flow liquefaction failure occur? There are a whole lot of reasons. There are a whole lot of things wrong with the dam, there's no doubt. Damaged the original starter dam. That resulted in increased saturation of the tailings, very rapid deposition of slimes, and the slimes were deposited closer to the dam than was intended. Failure of a concrete drain and the setback of the left abutment caused the dam to be raised over slimes. You're putting the raising further back down the beach. Compression and lateral extrusion of the slimes and loosening of the sand layers above. Why did the flow liquefaction occur where it did? It occurred at the setback. So setbacks, in many cases, don't actually lead to stability. They actually might well make stability less than it would be otherwise, because you're moving down on slimes or finer grained materials that are softer and wetter. Why did the flow liquefaction occur when it did? There's a bit of conjecture. If you look at the expert panel report, and in particular read the last paragraph in the in the executive summary, you'll get something like this, and I've paraphrased it a little bit. There was a series of 3 small, closely spaced or closely timed earthquakes within about 1 kilometre of the dam, about 30 minutes prior to the failure. Now, they weren't big enough to cause liquefaction in themselves, but they were closely spaced. They would have some sort of cumulative effect. Small deformations were sufficient to initiate liquefaction of the marginally stable setback that was experiencing lateral extrusion due to the rapid rate of rise of tailings. It was up to somewhere between 2 and 4 metres per month, not 2 or 4 metres per year, which would be more common in places like Australia. So one of the resulting changes to tailings dam design in Brazil's wet climate arising out of Fundão. If you look at prior to Fundão, Brazilian law required only drained geotechnical stability. They actually call it effective stress analysis. It's a very short paragraph in the law. It's not a how-to guide. It just tells you, you must do this. The drained internal friction angle can generally be relied upon and only varies by a small amount, possibly plus or minus 3 degrees, provided it doesn't go to residual strength. Drained geotechnical stability is generally not critical. Undrained or seismic geotech stability likely governs, as was the case for Fundão. So arising out of Fundão, and by 2017, the Brazilian law was changed, and it now requires undrained, drained, and post-seismic analyses. But it raises some questions. What are reliable and representative peak and post-seismic undrained strengths? In Brazil, they weren't used to coming up with these, and they've struggled. Undrained strengths also vary more widely than drained strengths, implying less certainty about the calculated factor of safety. So if your undrained strength varies by, say, plus or minus 30%, depending on which consultant you ask, your factor of safety will also vary by that amount. In the Latin-speaking world, as opposed to the English-speaking world, simplistic pseudostatic stability is analysed. If any factor of safety values are less than required, I would say, and most people would say, do a deformation analysis to check freeboard and how much movement you might get. Now, the Latin-speaking world, I'd make the point, is different from the English-speaking world. The English-speaking world, tailings design is governed largely by guidelines, such as the ANCOLD or CDA guidelines. In Latin-speaking countries, it's governed more by the law, which says you must do certain things. But it's not a how-to guide. Turning now to Cadia, March 2018. Again, a foundation failure. Prior to the failure, there was a pond at the toe where the slump location occurred. So well prior to the failure, there was only the northern tailings storage facility, the southern one, which is in the bottom half of this picture, had not been built at that stage, but there was a pond, there was a low point right against the point or the toe where the failure subsequently occurred. Now the pond, there was a pond there from natural sources. There was also a pond from the tailings that came from the Southern Tailings Storage Facility, right in the same location, at the maximum height of the Northern Tailings Storage Facility. Again, turning to the expert report, technical causes of the Cadia failure. Why did the event occur? It's interesting they called the failure an event rather than a failure. Deformation in the foundation during construction of the upstream stage 10 and the upper buttress and excavation at the toe led to the removal of embankment support at the toe and later liquefaction of the loose saturated tailings behind the embankment. So liquefaction was a secondary event. It was about a day later. Why did the event occur when it did? Where it did? Again, there was a weak, highly compressible layer that was previously unknown. The local height of the embankment at that point was 94 metres. The prevailing phreatic conditions, near saturated tailings against the embankment, also contributed, and there was excavation at the embankment toe. Why did the event occur when it did? Timing was controlled by deformations accumulated through the construction history. So essentially it was a construction-driven failure, which was sufficient to trigger foundation failure and later flow liquefaction in the loose, near-saturated tailings stored in the Northern Tailings Storage Facility. There was a small earthquake, or a series of small earthquakes prior to the event, but they were ruled to have no effect on the failure. They also asked the question, why won't a similar event occur? A similar failure can be avoided by adequate analysis of the foundation conditions, well, investigation first, then analysis, and appropriate instrumentation to demonstrate that the foundation is behaving as intended. Now, looking at the failure, it was a relatively small-sized failure. You can see an aerial view of it there. And then in the lower diagram, you can see the location of, well, first of all, stage 10 was back here. There was a tension crack that developed here. The so-called upper buttress was placed here. And just giving a bit more detail of that, you can see the stage 10 up in the top right-hand corner. It was constructed, then the upper buttress. The intention was to add the two downstream buttresses, the toe and this face buttress as well, but they weren't done at the time, and there was excavation at the toe instead. And that caused the failure. If you look at a cross-section here showing the excavation at the toe, they went through about 4 meters of tailings. These are the tailings that came from the Southern Tailings Storage Facility. It was the end of their beach. And finding relatively poor foundation conditions, they dug a pit to investigate a little further. So you've now got loading at the crest and you've got unloading at the base. Most people would realize that that was a bit of a recipe for disaster. And because it was known by that point, I guess, that they'd found weak foundation conditions. It wasn't known prior to the excavation. Some useful information came from satellite INSAR. There was displacement monitoring just from prisms. If you look at the crosses, you can see that they're anywhere up to about 5 months apart, so certainly not particularly frequent, but that was fairly common at the time. So that's survey. And then INSAR, which was calculated after the event using satellite imagery, is the green dots, and the failure occurred about there. So you can see that this was compared with a flow liquefaction failure, this was a relatively slowly developing failure because, of course, INSAR only gives you a point every 5 days or so if you've got ascending and descending, or even more infrequently, about 11 days if you've got only descending from the north to the south. The other thing you might look at is the loss of foundation strength going from the peak to the remolded. We can look at this in terms of laboratory strength, or we can look at it in terms of strength ratio and factor of safety. So looking first at laboratory strength, that first laboratory test shows a 23% drop going from the peak to the remolded, and about 28% in the second case. If you look at it in terms of strength ratio and factor of safety, the normally consolidated value, more or less back calculated, was 0.22, corresponds to the factor of safety of 1.15. But of course, at failure, the factor of safety is 1, and you bring that back to this line, you come down to a value of 0.145 as the strength, the undrained strength ratio. 0.145 was the actual value. The value used, would have been used in design, was more like 0.22. So that's a 34% drop. If you do it in terms of factor of safety, it's a 13% drop. You can see there's quite a considerable drop just based on those two simple analyses of laboratory strength and strength ratio versus factor of safety. Gives you a bit of a feel when the deformation exceeds a certain point, how much drop in strength, drop in stability you might get. Now turning to Brumadinho, January 2019. Another flow liquefaction. So we've got two foundation failures, Mount Polly and Cadia. We've got two flow liquefaction failures, both in Brazil. That is Fundão and Brumadinho. Most people by now will have seen the little video clip, and this is just a shot taken some seconds after this tailings dam liquefied, killing 270 people. We can be much more precise about the number because we had the advantage of DNA testing. You don't find whole bodies. Unfortunately, you find body parts, and you need DNA to identify them. The dam was about 80 meters high. The wave that came out was at least 30 meters high. Again, turning to the expert panel report, Dam 1 was marginally stable, basically too steep, too wet. A sudden strength loss and resulting failure of this marginally stable dam was due to a critical combination of ongoing internal strains, or creep, and a strength reduction due to the loss of suction in the unsaturated zone as it wet up with rainfall. The rainfall we're talking about was not the highest on record, but the preceding 6 years up to this point, the rainfall was progressively increasing each year. So this particular year was quite a high rainfall event. It wasn't, or high rainfall wet season, it wasn't the wettest, but it was quite high, much higher than previous years. And the calculated pre-failure strains from this combination of triggers match well the small deformations of Dam 1 in the year prior to the failure. Of course, it took off and failed very dramatically when it did fail. It's also interesting that limit equilibrium analyses assume all points on the slip surface to be at the same state. This is not necessarily true for a marginally stable dam. It's clearly not true in this case, where different parts of the tailings mass are at different states on the stress strain plot. Some are pre-peak, some are at peak, some are post-peak. And the drop-off in strength after peak is very dramatic in this particular case. So a schematic of the path to failure of Dam 1 looks something like this. This is undrained strength ratio versus vertical strain. The tailings material had a very brittle behavior. At about 1% strain, they collapsed. Normally consolidated would be more like the dotted line. So essentially you had this combination of strength reduction due to loss of suction in the unsaturated zone, where most of the rainfall infiltration was taken up, didn't get through to the water table, and ongoing creep under constant load. This was constant load because the dam had ceased tailings deposition. And I could put those two vectors anywhere. I could have put them down here and had loss of strength and creep. It would have had the same sort of effect, a reduction in strength, leading to that sudden flow liquefaction failure. So that led to the global industry standard on tailings management. Its aspirational goal is zero harm to people and the environment. And of course, we must realize that zero harm is impossible. So it's an aspirational goal. The design intent is to have extreme consequence classification and a 1 in 10,000 year return period for both flood and earthquake loadings. That design intent matches exactly what we have under ANCOLD and CDA, but for closure. So essentially it's trying to bring that requirement to the operational phase. The trouble is the current operational practice is typically maybe 1 in 100 or 1 in 1,000 year return periods, not 1 in 10,000 years. So the implications are that we should really design for the probable maximum flood. We should design for the maximum credible earthquake, and it doesn't matter where you are in the world, that's likely to be sufficient to liquefy susceptible materials. We should design a stable tailings landform with negligible risk of credible failure modes. We should then dewater the tailings to reduce their volume and hence get away with a lesser dam, and also to increase rehabilitation and future land use. So basically have a disconnect between storage or containment and storage and get the two working together. So how has the industry responded? The late Andy Robertson in 2018 in Brisbane said, in the wake of recent tailings dam failures, improved management resilience, that is governance, is leading over improved engineering resilience. If we had the latter, we'd actually be reducing the liability. So governance alone can't do that. And then further, the response to the global industry standard on tailings management following the catastrophic Brumadinho failure has largely been improved governance. How much have we actually changed the way we manage tailings? I think the plot by Silver is a very pertinent one because it highlights the disconnect between factor of safety and probability of failure. So if you choose a factor of safety of 1.5, but you have poor design and construction, you've got a 1 in 10 chance of failure on an annual basis, a 1 in 10 chance. So in other words, out of 10 dams, 1 will fail. Clearly, we're not there because we don't get that failure rate. We can adopt the same factor of safety, but have best practice design and construction and reduce that probability to 1 in a million. Clearly, that's where we need to be. If we look at upstream construction, it has limits even in a dry climate because eventually you'll be founding on wet, soft tailings. If we look at this cartoon, there's a starter dam. We put in tailings behind it, we have a pond, we raise it upstream, tailings in a pond, and so on. So what we have is an advancing edge of the pond. But if we keep going, then it's clear that that advancing downstream crest is going to be at some stage sitting on top of a former pond. In other words, wet and soft tailings. What about construction on weak foundation layers? It has limits as well. As the height of the tailings dam is progressively raised, the pre-consolidation pressure, the highest historical stress of foundation layers, we're talking about soil layers, may eventually be exceeded. So the foundation layer then reverts from over-consolidated to normally consolidated. Its stiffness is about a factor of 10 lower, and you're going to get much more, 10 times the deformation for an increase in load. And such deformations can threaten freeboard, potentially leading to overtopping and failure. Examples: Asnocola, Mount Polly, and Cadia. There's some sort of evolution of tailings dam construction. As we started with a trapezoidal or trapezoid support, if you like, a trapezoidal downstream tailings dam raised by a series of raises downstream. We moved to upstream. But we're essentially relying on substantially on a tailing zone. What we've really created is something like a skin on the upstream face, but the tailings behind have to provide support. Now, in regions where upstream construction is being banned or it's unachievable, we want to go back to a conventional tailings dam, we need a trapezoidal downstream tailings dam, at least maybe a centerline dam you get away with as well. And then there's a lot of talk about moving towards a filtered tailing stack. We have to stop calling it a dry stack because it's not. It's filtered tailings that to some extent are being compacted as well. And if we have a structural compacted zone, we're still relying on a substantial non-structural zone. And if you compare the top right-hand corner with the bottom left-hand corner, it looks somewhat similar. So in regions where upstream construction has been banned, you wonder how long it's going to take before we ban this sort of filtered tailing stack. What are some alternatives? We should be separating tailings containment from storage. We should simply build stable dams. We should maximize the use of the storage volume by dewatering the tailings, saving on dam construction costs. They'll also reduce the tailings footprint and the height, and they'll maximize the post-closure land use potential and ecological function. You could consider an integrated waste rock tailings facility. It could be located to minimize total transport costs of the waste materials. It could adopt a simple cross-section. It could be constructed incrementally, a stable landform or waste rock buttress with negligible credible failure modes, and the stored tailings could be thickened to a slurry through to compacted filtered tailings, whatever your budget will allow. You could also consider in-pit disposal where appropriate and suitable, but preferably dewatering the tailings to maximise the storage capacity and to facilitate rehabilitation. How would we make a filtered tailing stack more stable? And here's a suggestion. Ensure the stable containment of filtered tailings using a combination of an earth or sand dam with an inner structural zone of compacted filtered tailings, taking away any reliance on non-structural filtered tailings zones. So going from the top to the bottom. Now, in fact, in Brazil now, they're required by law where they use filtered tailings to compact the entire stack, not just an outer zone. Let's think about what a tailings facility might look like. Typically in Australian conditions, you have a starter dam, you go to a downstream raise, then you decide, oh, there's too much fill involved in going downstream again, so we'll go upstream. Now we're worried about upstream failure, so we put in a bit of a berm, which is not a very efficient way of stopping upstream failure. We go one more with a bigger berm and a longer berm. But how do we make that close? Well, to close, we need a stable post-closure landform. If we built that, we'd then have a zone here to infill. And the total amount of fill we'd have used to create this stable post-closure landform is now more than if we just did this in the first place. Just build a stable trapezoid in the first place. Something like this. So some key takeaways. Tailings dams that fail are marginally stable, and there is typically a combination of causes, and obviously water is the key element. If the tailings were dry, you wouldn't have a stability problem. Fatal tailings dam failures can bring real change. El Cobre revolutionized tailings dam construction in Chile's highly seismic setting and also spread to Peru. Brumadinho led to the GISTM with the ambition of zero harm from tailings facilities, affording operators flexibility as to how best to achieve this goal. However, the GISTM has led primarily to a focus on governance rather than changing tailings management. Alternatives include compacted filtered tailings and integrated waste rock dumps, tailings facilities. Separate tailings containment from, and then have optimal storage. Separate tailings containment and optimal storage. Will we improve tailings management sufficiently to recover confidence and trust? Over to questions.
Thank you, David, for your insightful presentation. We have a question from Oli. In the NTFS displacement, how long would you say that the time from possible detection to breach was? Can you address this, please?
It was, they knew things were happening. There was cracking at the crest, there was deformation. They had plenty of time to get everyone off-site, out of harm's way. In fact, it was probably about a day at least, maybe a bit longer. In fact, they tried to get some ground-based radar here on site, but couldn't get there quickly enough. It was requested the day before the failure. Couldn't get it there quickly enough, and the failure occurred anyway. So they had quite a bit of warning. Very different from a liquefaction failure where you have virtually no warning and it happens in seconds.
Yeah. Thank you. Another question from Oli. In the Bermudino case, could you give an estimate on how long before the failure occurred it would have been possible to foresee the failure?
It was impossible. There were no precursors to the failure. There was no warning. There was nothing in, despite what you might read in some of the papers that have come out subsequently, there was nothing in the satellite INSAR analysis that showed it. They didn't have INSAR analysis before, it was done afterwards, but there was nothing in that that would have shown a precursor to the failure. They had prisms, but the survey or the survey location was too far away from the dam and the precision wasn't high enough to pick up anything before the failure. They had ground-based radar, but it was interfered with too much by, or there was too much noise from moisture on the slope. It was a well-grass slope. It was variably cut grass. It had wet spots. There was ponding on the setback and so on. So ground-based radar would not be very good in that environment to pick up the small movements that might have been occurring pre-failure. There was seismic monitoring, but there were no blasts at the time. No earthquakes either, so there was nothing there to pick up. There was nothing in the piezometers that showed an indication of failure. But of course, when it took off, all of those things would have been triggered if they're capable of being monitored at all. There was a seismic response to the failure. In fact, there were a couple of seismic responses to the failure, but they happened after the failure initiated. Next one.
The next question is it possible to substitute the waste rock buttresses with geotubes filled with dewatered tailing as the later might be cheaper? Will it provide the same amount of stability?
Well, I wouldn't say it would give you the same level of stability. Very few waste rock dumps fail, whereas there have now been a few filtered stacks that have failed. So not necessarily the same stability. But there's nothing to say that you couldn't use the two in combination. So you could use a certain amount of rock and you could have I would say preferably on the inside because tailings are erodible. You could have well-compacted filtered tailings on the inside to add to your stable trapezoid of support, if you like. Certainly do that. You could also potentially use sand. There are many successful sand dams, particularly in Latin America. And you can ensure their stability by making sure that they're constructed downstream and they're robust. They've got relatively flat side slopes.
Okay. Another question would be, what will be the cost to include an embankment dam to stabilize filtered tailings deposits?
I'm not sure I exactly understand the question, but
yeah.
I'll have a bit of a go anyway. So it depends. You can easily mount an argument that dewatering of tailings obviously becomes more expensive. The more you dewater the tailings, the more expensive that exercise will become. If you look at that in isolation, you would say you would never dewater the tailings. You would never filter the tailings. It's just too expensive. But you've got to look at the whole thing holistically. So if you ask the question, can you tell me what proportion of your tailings deposit, your conventional slurry tailings deposit, is water by volume? Most people don't know. But for a typical metalliferous mine, it's at least 50%. So 50% of the height of the dam is there just to support water. Obviously, it's water plus solids, but half of that volume is water. If you go to the extreme of something like red mud from bauxite processing, if you deposit that material underwater and don't do anything to densify it, it will occupy about 85% of the volume is water. 85% water. So most of the dam that you build to contain that is actually containing water. Now, in the case of red mud, you can't reduce it to less than about 55% water by volume, but still that's a big improvement compared with 85%. Same with oil sands tailings. They for a while used to call them mature fine tailings. They gave up on that name and have reverted back to calling them fluid fine tailings because essentially they remain a fluid. So they would be probably 90% water by volume. So there's a huge cost saving in terms of stored volume or the use of an available volume for storing tailings by dewatering them. And if you do that, then you don't need to build anywhere near as high a dam for the same volume of tailings. There's a cost saving there. You've got to look at it holistically, not simplistically. Next one.
The next one would be, what are the most effective strategies to optimize tailings management without modifying or upgrading the existing tailings dam structure? Are there specific practices or technologies you would recommend implementing to achieve these goals?
Yeah. Well, the fact is, the conventional approach, if you keep building a tailings dam higher and higher, you will continue to modify the way you design and construct it. It's just a fact. So you might go initially you'll go from a starter dam, you might do an initial downstream raise. If you can justify and make upstream raising work, you will do that. And you'll do upstream raising until that doesn't work, and then you'll start buttressing. And then the buttress will become eventually something approaching a centerline construction. And then for closure, a stable landform, you may have to go even further than that and essentially retrofit it to be a downstream embankment. So we make those changes already. What I'm saying is the drivers are a little bit out of whack. Instead of we should focus on what the closure landform will look like and think about, can we optimize the cost to get to that or maintain that throughout the life of the tailings facility, not just try to retrofit it at the end, because at the end it will cost you much more. Next one.
Yeah, next one. You mentioned that Bermagino was creeping over a relatively longer period. Has any retrospective install work done to pick that up?
Yeah, so Brumadinho was slowly creeping. It was moving at about an average of about 30 millimeters per year in a direction roughly parallel to the downstream slope. If the movement was only down, vertical, it would be representing consolidation, but this was clearly moving very slowly down slope at about 30 millimeters per year at an angle. So that is of concern. Most dams would creep. We don't know by how much, and it's difficult to determine that. Some people try to use satellite INSAR. The trouble is that gets confused by all the construction activity and the deposition of fresh tailings, so you don't have a constant form of reference. It's better applied to a dam that is closed. It's better applied to a water dam, perhaps, where the dam isn't progressively constructed. So, yeah, a little difficult, but yes, most dams would creep. But that creep rate is nothing compared with the rate of movement during failure, which was grossly accelerated.
Thank you. Next question is, the current ANCOLD guideline is mainly for above ground TSF. How applicable is it for in-pit storage? Can we adjust the requirement in view of the relative low risk of release of the tailings?
Yeah. No, I think in-pit is very different, provided you don't go above ground, provided you don't have a situation where you could possibly get an overtopping. I think the key thing with in-pit, it's a bit too easy to do, and people tend to do it too simplistically. So they simply put a slurry tailings into a pit, which often has a cover of water, which means that the consolidation and there's no opportunity for desiccation, but the consolidation might also be limited because of the very fast rate of rise. You've got a shape that's near vertical compared with a very flat shape. So I think if you are using in-pit and you want to maximise the use of that volume, I would recommend that you dewater the tailings rather than put them in as a slurry. And you can deliver them dewatered by gravity. You don't necessarily need to try and pump them into the storage. You can simply do it from the crest and do it by gravity. And there are precedents for doing that. Kidston was doing that 25 years ago. Next one, or are we about over?
Maybe last one. What aspects of GSTEM might have prevented the failures you have discussed, given they weren't related to a major flood or earthquake?
Well, all of the failures that occur are for marginally stable dams. And the purpose of GISDM is to move away from marginally stable dams, and we should be. We simply should build stable dams. If we build stable dams, then the failure rate would be, you might not say acceptably low, but much more acceptably low than we've currently got, because we've got a failure rate that is unacceptably high and a fatality rate, which is certainly unacceptably high, and an environmental damage rate that's too high. So we need to move away from marginally stable dams and move towards stable dams. We should make that our focus. Thanks, Kathy.
Thank you. I think, Leonardo, can we ask one more question?
Yes, let's do that.
Yes. Okay. Do you recommend any lab testing modified procedures to measure creep while shearing?
Measuring creep. Well, we've got an increasing number of ways of measuring deformation basically over time. We can do it by prisms. We can do it by satellite-based methods, GNSS, analyzing satellite INSAR. We can do it with ground-based radar up to a point, but it depends on how wet the climate is that we're working in. In a dry climate, ground-based radar will work a lot better. And I wouldn't say we should rule any of those out. You could also look at things like fibre optics embedded within the tailings as they're built up, because often failures initiate. Part of the reason why we don't see them initiating is they're actually initiating in the body of the tailings, or even in the body of the embankment. And by the time it appears on the downstream slope or the crest starts to drop, it's actually too late. It's already been initiated. So the sooner we identified we had a problem, the better. So the idea of putting instrumentation within the body of the dam and or the tailings is probably the way we should be going. But there's no surefire way of predicting when a flow liquefaction might occur. And if it's an earthquake-induced liquefaction, we can't even predict when the earthquake's going to occur. So that's even more problematic. Thanks, Kathy.
David. Thanks, David. Over to you, Leonardo.
Right, thank you very much. If you agree, David, I would like you to go over the last question now before switching to Brett's presentation. And only if there are more questions, we'll continue with them at the end. I will read it for you then. At what stage would you move from limit equilibrium modeling to deformation modeling? Is limit equilibrium on its own sufficient if you are achieving certain factors of safety like 1.5 for peak and 1.1 for residual shear strengths?
Yeah, I think it's unfortunate that we've become so fixated with the factor of safety approach. It's a simplistic approach which is poorly understood. What does it really mean? It has the attractive word in it, safety, factor of safety. Probability of failure has the unattractive word in it, failure. But it doesn't matter what the factor of safety is, every structure has a probability of failure, even though it may be very small. It doesn't go away just because the factor of safety is above a certain level. So I think we should be using the factor of safety calculation, which is rather simplistic, really, when you boil it down, as a screening test. And ANCOLD and CDA and other regulations around the world are all saying that ideally have a factor of safety in excess of 1.5 for the peak condition, and have a factor of safety. Now, there's a little bit of disagreement about the seismic value, what it should be. In ANCOLD, it's between 1.0 and 1.2. That's quite a range. We don't give a range for peak, so why do we give a range for seismic? And there's a rider there that allows you to make a judgment as to whether your data are good or bad. In CDA, it's more like 1.1 to 1.3, but still a range. Some mining companies have adopted 1.3. I think we should have a little more uniformity on that, but whatever the figure is, we should use it as a screening test. And if your calculated factor of safety comes in below those screening tests, 1.5 or somewhere between 1 and 1.3, then you should do deformation analyses. But recognize that it's a very different analysis. You're talking about stiffness, whereas in the case of limited equilibrium, you're talking about strength. So two very different sets of parameters. But I think that's the way you should do it, and you should do initially a simplified deformation analysis, and depending on the results you get, move towards some sort of numerical calculation of deformation. And then you're comparing it against freeboard and other things.
Right. Thank you very much, David, for your presentation and for kindly answering all questions. Now we'll switch on to Brett's presentation. Let me introduce you to Brett, who specializes in projects related to mine waste management, specifically tailings dams, filter stacks, waste dams, water supply dams, and associated large-scale civil earthworks. Over his 35-year career, he has been the engineer of record or designer of record for several extreme and high-consequence dams, and has completed reviews and governance audits for numerous tailings facilities in Australia, Canada, Africa, Papua New Guinea, and South America. He is currently the convener of ANCOLD's Tailings Guideline Working Group, which aims to update the guidelines on tailings dams. And I think that this is the right moment for Brett's presentation because they have been working a lot to update the guidelines. Over to you, Brett.
Yeah. Thank you, Andra. We'll just share. Let me know if it comes up.
Yes, we can see your screen now.
Great. Look, mine's going to be a bit of a dry read because I'm really talking about a guideline that's in preparation and working on. So, look, what we're going to do is talk about and sort of anchor off some of the conversations that David just had, and we're going to try and put that into the guideline that we're talking about. So I'll talk about the Tailings Working Group. We'll talk about the current guidance, the future direction that we're looking to do with the updated guidance. And we'll talk about all the interfaces with ANCOLD and application to GSTM. And we'll talk about the new sort of approach to the guidance is like a process-driven dam safety management and performance envelopes. So, and it's best to sort of talk about that as we go. And we'll talk about a little bit of the flood management white papers that we're developing at the moment and seeking input from industry and ANCOLD as we do that. So look, I'll just go and, as I said, talk about the updated guidance. We're really a work in progress and therefore subject to change. So there's the caveat here. What you see here is still getting worked on, and we'll be seeking continuously between now and when it gets pushed out next year, we hope, feedback from all parts of industry and stakeholders to get ourselves a guideline that's going to work best for everyone. There'll be feedback sessions, and hopefully once we get this in a draft, some workshops to present that and take it out so people understand. A bit of a shout out to the Tailings Working Group. That's the group that's in there. That includes David, as well as a suite of other people from academia, consulting, industry, and regulators. And we're fortunate to have a very distinguished peer review group who ostensibly were responsible for writing the last tranche of the guidelines that have been very well received and used by industry. So just a bit of a brief outline on the guidance. The last update to the ANCOLD Tailings Guidance was 2019, and it was really just initial response to these dam failures that David discussed, and included a technical update on the Australian seismicity as well. Since then, there's been a suite of new guidance and standards that have come out. There's ANCOLD Bulletin 194, which is out in draft on tailings management, waiting for that to get printed. We've also got GSDM, which is a governance guideline, and the ICMM guides, TSM, and among others. So our update wants to include all this new guidance and clarify how all of these new updated publications would be applied within the ANCOLD framework. So just a quick point out on what we're trying to do here. So obviously the tailings guidelines are here. I'm not sure if you can see my mouse, but I hope you can. There. So it's really a guideline. So the key thing for us is a tailings dam is basically a dam. So we're going to design in accordance with the dam safety management principles and the DSM guidance that's out. So one of the things that's complicated our preparation of this document is the DSM guidelines are actually doing an update right now. So we're trying to write our guidelines referencing back to the DSM guidelines, so we're not repeating guidance while we're doing it in parallel. And they're just at the stage of getting their document written now. So we're sort of dragging behind them about 4 to 6 months, we would think. So the object is we're going to be referencing back to these core documents of dam safety management, risk assessment, consequence category, design for earthquake, acceptable flood. We're going to use all of the same basic engineering processes for a tailings dam as we do a dam. And then in addition to that, we'll have all of these additional guidance that are applied to the specific requirements for a tailings dam and the complications we have. So this there shows all these new guidance that's coming out now in terms of the dam break consequence assessment, the dam safety emergency plan, and the foundations investigations. So that's to be done. So we've been asked a bunch of times as a group, are we adopting the GSDM guidance? Are we changing the way we do consequence categories? And the answer is basically no. And for the reason that we're anchoring to the ANCOLD guidance and the work that the consequence categories are there. So we're not going to be changing consequence categories to align with GSDM. That doesn't make sense for us. We're wanting to link into those guidance. But using the updated guidance and the current guidance of ANCOLD doesn't conflict with GSDM, and I think the industry is used to dealing with that. We have our ANCOLD consequence category, and then we obviously have the GSDM consequence categories. And I think the dual reporting of that is not confusing anyone at the moment. I think that's been understood by people who are applying GSDM guidance. So the current guideline shows a phase-driven guidance. So this is a pretty poor picture, but it's the only one I've got, and it just talks about the different phases of engineering for a dam. And so we see that as it's fairly positive. But what we're looking to do in our new guidance is to move from this phase-driven guidance, and I don't believe this is what was intended by the authors, because obviously this is the process for designing the dam, but really this is the dam, as David alluded to, from cradle to grave, not doing this every single raise, right? So really it's feasibility planning for the dam from initiation to closure and then running through the whole process. So we're going to reinforce that in the guidance, because we don't advocate running this on running raises where you do a feasibility planning and a design for every incremental raise. Really, we want this looking like that process for the whole dam. So the new framework, and you'll see this picture evolving from time to time, is really the guidance for us is in this dotted line, and really what we have here is working out, do we need a dam, yes or no, And we have this box outside here, which is really talking to some of the questions that David was posing. Is, do we need a dam? Can we put this in pit? Is there another better way to remove these risks and not have a dam? And then really you go to the ANCOLD guidance on tailings dams when you need a tailings dam. So in the box here is actually how we frame the guidelines. So are we able to make decisions to reduce the risk or reduce the consequence? Can we put it in pit? Very good question, right? But once we get to this decision made that we need a dam, then the box, the dotted line here represents what we're going to be doing there. So obviously, you know, can we reduce the risks? Can we reduce the consequence of failure by doing a downstream embankment rather than upstream? All of those things that get there. And then once we've done that, that sets our framework for the dam. And then we really set these performance envelopes. And we've used the frame as a performance envelope because we want to come up with a way where here's the performance envelope. So here's our critical, here's a failure mechanism that we need to manage. Here's the performance envelope that we need. And then here are the things that need to happen for us to meet this performance envelope. So effectively, we have this Deming cycle. So here's what we need to do to get the acceptable risks on this dam for the dam. Here's all these elements that we need to do. We need to check as part of our process. Are we meeting our performance envelope? If not, we've got to go and change it and rectify it. It's not really a complicated cycle, and we've really just taken a lot of the boxes that were in the previous guidance and made it into the sort of Deming cycle, because really that's how tailings dams are built. We start off with a plan, we build the dam, we execute, we measure. Are we meeting our plan? If yes, that's great, we continue on. If not, we stop and we revise and we work out what we need to do. And sometimes that means building a buttress, sometimes that means stopping the dam short of where we would like it to be, or changing the process. So I can take some questions on that, because I expect we'll get some based on the feedback we had from the WA Tailings Group 2 weeks ago. So I heard the question to David, and you'll probably get it to me again. In these guidelines, we're really talking to the term tailings dam is going to refer to a constructed structure or embankment to contain tailings. So we're really looking to what those dam structures are, and we're not specifically going to provide detailed guidance on things like in-pit storage, filter stacks, and integrated tailings and mine waste dumps. So our intent and our thoughts are at the moment that we'll provide some commentary in the back of the guidance on how some of the guidance for tailings dams may be applied in certain situations for say things like filter stacks and integrated tailings and mine waste dumps. But they're not going to be exhaustive, and they're going to be guidance only, and we'll be trying to direct people to make their own judgments based on the standards, because these standards are really not applicable for in-pit storages directly. You just need to, you're going to need to use engineering judgment, and they're probably going to be out of scope for most of the things. So look, we'll talk about this performance envelope example using this chart, and I've specifically put in an example that's based on, say, deformation, just to talk through one element, and recognizing the performance envelope is not going to be just one element. It's not going to be just factor of safety. It's going to be deformation. It's going to be scour management of the spillway. It's going to be how much freeboard we need for floods. So there's going to be multiple performance envelopes. So obviously you can see when we do this, we need to run it through. So this one's going to be a very simple one, and it's going to be a performance envelope on a pretty simple dam, which is a downstream dam with a satellite dam built on a soil foundation. So as an example, and apologies to people in WA saw this before, but we're just repeating it. It's our post-construction. We've got a dam. We expect post-construction settlement of this dam to be 600 millimeters. So the design includes a camber to compensate for the settlement of the foundation. So that's our expected performance. So the storage and the flood handling of this dam is based on this expected performance of 600 mils, and our freeboard's being built into it there, along with the storage of the tailings. So all of that forms our expected performance envelope. We've put instrumentation on the surface to monitor this as part of checking and doing that. And that's what we've done as part of the performance verification. So there we have, here's our performance envelope. You know, we've defined our performance, and we have our characterization, our design, and our construction for doing the verification. So not very complicated. We do this all the time. It's just a different way of saying it. So as with all things with tailings, we you know, plan, do, check, act. So we've built this thing, and we've now gone and looked at our instrumentation. The dam settled more than 600 mils. So we've gone back and checked it all. And what we find out, this additional settlement now compromises our flood handling capacity. Our freeboard's no longer what we had in our design envelope. So what do we do? So now we've got our performance monitoring, we have our surveillance and monitoring. Is it within our envelope? And clearly it's not. So we now go to what we call rectification. So we're going to have to repair the dam. Now that doesn't mean we're going to repair the dam every time. What we want to be doing is going back and looking at the crest. So potential options for this dam, because it's a very simple example. Let's just change the dam. Let's build the crest up for the differential between it. So we've got 800 mils of settlement. We had 600. So can we top this up 200 millimeters, or can we change the performance envelope and reduce the tailing storage? Right. So these are all of the options that are always available to us as designers, and it's pretty simple, as you can see. Right. So really, what we said is that we can revise the tailings to be stored in it. We think that was the answer we sort of suggested out of the two, because we can't get out there because of piping and discharge and the thickness of the thing. So the new performance envelope's 800 mils of settlement. And what we've done is we've reduced ostensibly the volume of tailings stored by 200 mils. So therefore, we've done this rectification. We've changed this performance envelope, and then we go back into this cycle to check, right? So this is really nothing new. It's just some different terminology, and that's where we work. So now our performance envelope is now 800 mils, 200 mils higher than it was. We didn't do the raise. We've got the same freeboard because we've reduced the tailing storage, and then we're looking to increase monitoring because basically this additional settlement wasn't sort of foreseen. So do we have unfavorable cracking? Review the instrumentation in light of that, and then check the changes don't influence other performance envelope criteria, right? So I'll take some questions at the end on that one. I'm sure there's probably a lot. We'll talk about the flood management guidance, because this is one of the elements that's going to go out in a white paper very soon from 3 in our working group, Michael Ashley, Jay Rana Saraya, and Ryan Singh, to inform the guideline. So we'll just go back to what we did. About 2 years ago, there was some industry feedback and questions that were given out to the groups as part of the review on flood management and water management. And some of the feedback we got was there's a misalignment between the tailings guideline, or a perceived misalignment between the guideline and other ANCOLD guidelines, and really the dam failure consequence category for tailings dams versus sunny day, and the flood failure consequence category, and the AEPs in the guidelines versus the tailings guidelines were not aligned, and seemed to cause some confusion in industry. So there was some unclear guidance on some items, and the design flow chart in Figure 5 of the current guidance was pointed out as confusing, and some issues on spillway requirements. So, and what we also have is some inconsistent terminology between the tailings and other ANCOLD guidelines, just basically as these things have evolved. And what we're wanting to do is align everything back, so all of our guidance refers back to the core ANCOLD guidance as a starting point, and then, unless told otherwise, you design to those guidance. If we need to change it, we'll put it in the tailings guidance. So the proposed updates that are going to come out of our flood management guidance in the white paper that you should see soon is that the TSF owner is responsible and accountable for managing the flood impacts on the TSFs, right? ANCOLD provides the guidance, but it's not going to be a prescriptive approach, and that's typical of all ANCOLD guidance, you know, using risk-based assessments and engineering judgment. We want to clarify the difference between the flood management and the operational water management and clearly distinguish the two in different chapters. So we're going to actually write a chapter on flood management and we're going to write a chapter on operational water management so that they're clearly separable and make sure that the definitions and terminology there for each of the consequence categories are clear. Our current thought is we're going to remove references to environmental consequence category, right? And the reason for this is that the environmental spill consequence category is really part of the performance envelope, and that's something that's usually mandated as part of the licensing, and that forms an input into the performance envelopes. It doesn't really change the consequence category of the facility and what we need to design it to. So, you know, we're really looking at those floods and sunny days and flood failure envelopes to design a consequence category 2. And of course, we're going to improve the reference to the other guidelines and hopefully simplify the guidance by not having to repeat it. We're going to clarify the guidance intended for TSS with confining embankments and other facilities, in-pit and dry stacks, are probably outside of our guidance, but can be applied with judgment and due diligence. We'll include a discussion on the geotechnical design, structural design, construction, maintenance, and flood management, and look at simplifying the guidance to align. All right, that was pretty quick. The last question there, Kathy, is one of the things we don't do as ANCOLD and is that we have a tailings interest group where we send details to people, and we usually don't send that out. But if you want to be part of the tailings interest group in ANCOLD, if you send an email to tailings@ancold.org.au, we can add you to that group with your permission. So, and then you'll be able to get these updates from those facilities as well. Thanks, Kathy.
Thanks, Brett, for your presentation and the update. We have a question from Marcelo. Will the new guideline define what a dam is? It would be useful given the trend of adopting in-pit deposition, filtered stacks, integrated mine-based landforms, commingled co-disposal, etc. Follow-up question is, when does a dam stop being a dam? Are tailings encapsulated within downstream built embankment of, say, 300 meters still a dam? You are muted, Brett.
Yeah. So the answer is we aim to give some framework to what we think tailings dams will comprise and not comprise, and we'll provide some basis on how they can be applied to other facilities. But basically, they're going to be dams and those facilities, so integrated landforms, because you can't. I don't think you can routinely just apply them to a waste dump, if that makes sense, Kathy. So,
Yeah.
Does that answer your question, Marcelo?
We move on to the next question from Malcolm Barker. There is a comment and question. Your example is relatively simple, but an easy option would be a simple safety berm of 0.5 meter high to accommodate the wind wave overtopping. Would this be considered appropriate?
I think, Malcolm, the answer is yes. And we deliberately tried to limit the degrees of freedom on that, if that makes sense. So yes, the idea is that it was meant to be very simple, so we didn't get into the minutiae of it all. But the idea is that all of those options are available, and the intent would be to provide a suite of things. And I think the key takeaway is that we want to be selecting those options that remove the risk of failure, right? So if we put something simple in, we should be also looking, how does this reduce the risk of failure for these things as well? So it's not just coming up with the simplest, cheapest option. Sometimes it's actually coming up with an option that gives you the reduced consequence of failure as well. But yes, it was simple, deliberate.
Thank you. Does that mean that table 3, 4, and 5 will be removed from the guideline and no commentary regarding preventing a spillway discharge and the subsequent consequences will be included?
I believe so. I think we've been debating this, but so we should be saying that we should be looking to prevent spillway discharge. We're not saying we don't believe we should be preventing spillway discharge, but we're saying we're going to talk about the consequence of that as a design basis. So we will be modifying the tables, yes, but not removing guidance to remove that.
Is there a timeline for the update to the guidelines?
We've been linked at the hip with the DSM guidelines updates, and we're tracking behind them. We're hoping that we're going to have this out to people to review next year. Once that goes to review, I think our control of the timelines is tough. That's where we'd like to be. It'd be nice if we could get this out into people to look at this and draft next year. Would be where we'd like to be. Everyone cringes on the team when I start giving deadlines, because when you start doing these things and we start getting feedback, it takes a long time to get it from a thought bubble into something that's coherent and everyone sort of sees as consistently the same way.
Thanks. Will the new ANCOLD provide discussion on or guideline on wet sand stacks as well?
On wet sand stacks, was that you said?
Yes, that's right.
Well, we're planning to put some commentary in and provide guidance on where the tailings dam guidance may apply, right? So there'll be a commentary appendice in the back and where these things may be applicable and not, and sort of provide that. But we're not going to be providing a recipe guideline on how to design filter stacks in the tailings dam guidance, I suppose, is the simple statement.
Will climate change consideration be included in the new guideline?
It should be, because it's in the consequence category design, and I believe that we use Australian rainfall and runoff in dam breaks to work that out. So intuitively, we need to do that. It's part of planning, right? So climate change needs to be applied to to our planning, and when we think about these facilities, they're multi-decadal structures, so we have to apply climate change into them. So where structures are designed for 50, 60, 80 years, some of them, we have to be thinking about how, if warming's going and the spillways that are there, right? So I think it's implicit in what we do every day now. So I think our guidance needs to reflect that.
Thank you. Surely operation of water management is part of the rainfall flood management continuum. Can you comment on Malcolm's question?
I think I understand what Malcolm's saying. He said, how can we separate operational water management and flood water management? The answer is you don't in reality, but what we want to do is separate the design for each of those elements, Malcolm, is the plan, so that people are understanding clearly what design for operations looks like, and in order to meet our performance envelopes, and then design for what flood management looks like as well. So we sort of stopped this sort of blended sort of design basis. And that was the feedback we got from the membership when we went out and asked.
Okay. Next question is, flow liquefaction failures won't allow for the performance loop to be executed. Is there further comments on that?
Yes. If I go back to that first point, they should be designed out as part of the envelope. So if we go, I've stopped sharing, but really, if you look at that guidance, I'm not sure if you can see that, Kathy.
Yeah, we can. Yes.
Right. So really, this is the overarching risk decision. So this box here is something that we've just added in to the box, and really, you need to design those risks out, right? So it's and that's part of the commentary that we'll put in. But once you've decided what you're going to do, but we should be looking here to remove these flow liquefaction failure mechanisms and eliminate them first. So this box is really about we need to be eliminating these things before we start designing. So those, for example, if we think this material is going to flow and liquefy, we need to eliminate that failure mechanism by building a proper embankment to stop that flow or that liquefaction happening and threatening the stability of the dam. Does that
For
make
your
sense?
response. Yes. We move on to the next question. Is there any update on real-time monitoring system against failure modes of tailings dams?
It'll be included as part of the commentary because obviously this performance envelope requires people to understand how to do that. So, you know, our preference is not needing a real-time failure monitoring system to define the safety of the dam. We'd rather get it back to simple, right? So I think in all of these things, if you're sitting there and you're relying on a real-time performance monitoring system for the safety of your dam, that's a problem. I'd rather us design something that's much more simple and more robust and has a lower risk of failure, right? So I think the intent is with this is to understand our risks of failure and understand our probabilities of failure and then work ourselves to a point where those risks are reduced. And rather than relying on technology and really cute design, sometimes we just come up with something that's really simple. And I think that's probably paralleling how David was portraying these things. Why would you build something that's really slick and requires all of this heartache and anguish from the designers when you can just build something that's very simple and stable and has much lower, you know, orders of magnitude risks of failure and much lower costs of operation and maintenance and risk to the to the owner and the public, and allows you to close it much easier. So I think that's sort of the framework that this is going. So, you know, before you go into this loop of design, we want people to go into this loop of risk management, if that makes sense. Because you don't want to do that in the design process. The design process is we reduce all the failure modes and then we do the design. And then that design is focused on those failure modes that we just can't get rid of or reduce.
Thanks for your response. The next question is that will the revised guideline include any discussion or commentary on how or what the process is to decommission a tailings dam following closure?
We hope to, but I think that's really about, you know, the decommissioning and closure is going to be focused on dam safety, Kathy, not on all of the other elements of it, right? That makes sense. You know, it's a technical dam safety guide. There's a lot of other facets to closure that are not part of dam safety and are probably outside the scope of what we're looking at it in this document.
Thank you. Another question from Malcolm. Are you requiring quantitative risk analysis or can qualitative risk assessment be acceptable?
I think we're not requiring, I think we want risk assessment. We're recommending that we use risk assessment, Malcolm. And, you know, I think we require the practitioners to work out what's appropriate. So there's no requirement for quantitative at the moment. We're just suggesting risk assessment.
Good. Does the Australian rainfall and runoff data incorporate considerations for climate change? If so, is it necessary to conduct further assessment for climate change impacts?
I understand that the recent update in August for Australian rainfall runoff has included that, and we're assuming that people are going to use that updated guidance as part of consequence category assessment and selection of management of operational water and an extreme hazard, you know, flood waters as well. So we're trying to link our guidance back to the consequence category and dam break guidance that's with ANCOLD as much as possible. We're trying not to reinvent the wheel.
Okay, and last question is, will the update include the clarification that ANCOLD dam failure consequence category is not the same as the GSTEM consequence classification, and ideally an explanation as to how they differ?
No, we're just gonna say these are the ANCOLD guidance, ANCOLD consequence categories, and they differ from GSTEM, right? Because we don't know what GSTEM may do in the future, Kathy. So we're saying these are the guidance, this is the framework we use in Australia and ANCOLD and in these other publications. So the plan is to basically link it to that and probably not really talk about GSTEM, because I think the industry knows how to add the GSTEM work.
Another question, Brett, for you. Are the risks used in the design include any further risks?
Sorry, I can't say that again.
Are the risks used in the design include any further risks? I'm not sure about the question.
Yeah, no, I'm not sure either.
Please, do you want to rephrase your question?
Yeah. Look, I think when we did that, we only showed one element, but really we're assuming there's going to be a laundry list of design parameters and risk assessments that need to be worked through as part of every design. So, you know, the key opportunity here is that if we define, our thinking is that if we understand our risks and we reduce our risks at the start, we end up with a better design, right? And our design needs to look at life of facility. And then once we've actually understood our risks and we understand how we can manage them and how we build the dam, we then use this process to check that we're meeting our criteria and understand how that affects the performance of the dam. And we amend the design or amend the way we operate the dam to keep ourselves within that risk tolerance that we've set up. And if we do have something that's a deviation, the system documents it as management of change, which I think is a key point, right? So we have this initial starting point, and then we move. And all these dams, just about every tailings dam that's really old has changes to compensate for things we learn as we operate and build.
Thank you so much, Brett, for your presentation and response. We have 2 more questions for David, if he's available.
Sure.
David? Yeah, let me just find the question. Based on past experience, have any monitoring methods in situ or remote been useful for predicting failure location and onset times?
Well, I sort of covered that in a previous question and answer. Interesting, you know, Brett made the point, if we build robust, relatively simple, stable dams, the need for and reliance on instrumentation drops anyway. So that's a good point to make. But if you do want the added security of having some instrumentation, there's a range of different things you can use. Typically, we should aim for some redundancy. Like, for example, I had a discussion just today. People were talking about vibrating wire piezometers, and they're a bit concerned that, you know, is that the only thing you should do? And I think there's a consensus that you should not rely on just a single measure. And it would be worth having a number of standpipe piezometers that you can use to check when you've got unusual or anomalous results from your vibrating wire piezometers, because they do break down. They do give anomalous results at times. So it's worth having another way of checking. It's the same with everything else we do. You know, there's no silver bullet test for testing the undrained strength of tailings. So you should do a range of different techniques and compare and contrast the results you get. And that will add to your certainty about the parameters that you select. So that's a roundabout answer, but I think, you know, it's horses for courses. Build stable dams first, and then the need for all the rest diminishes.
Yeah. One more question for you, David. Can you comment on the emergency response to the emergency caused by the TSF failure on a few of the failures in your presentation? Can you focus on a strategy, tactics, chain of command, and the coordination format, and timeline of the emergency and the response of it?
Well, of the 4 ones that I focused on, only one, Cadia, actually had time put in place an emergency type response. So Mount Polly happened towards the end of a long weekend when most people were away. It was clear that they were not even inspecting the dam on a daily basis on such long weekends. Maybe there are other periods when they weren't doing it either. If they had, they may well have seen some warning signs of imminent failure, as they did at Cadia, because they're both foundation failures. But in the case of Fundão and Brumadinho, there was no warning. There was no time. It initiated and occurred in seconds. So there was no There's no possible way. And in fact, in both those cases, no warning was triggered. They did have alarm systems, so certainly at Bruandino. I'm not certain about Fundao. No alarm was triggered. At Fundao, there was actually there was actually someone who heard a boom and saw a cloud of what he thought was smoke. It's probably dust and or maybe water spray. I'm not sure exactly what. And he warned a large number of villagers to get out. And there's a little there was a mobile phone video of him obviously running up a hill, and he wasn't so focused on filming the event. There wasn't much to see anyway. It was sort of hidden behind a hill, but he was racing up the hill trying to encourage people to follow him. So there may well have been further deaths if it wasn't for that. But there was no formal warning given out.
Thanks, David, for your response. Brett, Keith just rephrased his question. Considering the designs are done focusing on the unknown risks, how are any further risks included to ensure that the design to accommodate those future risks, unknown risks?
Is this a question for me or Brett? We could probably both.
That's for Brett. That's for Brett.
Yeah. Have a go, Brett.
Yeah, so I think if they're unknown, we don't know about them. I think the key thing is when these risks are identified, we bring them in to the design envelope and we check against those risks, right? And I think, you know, using a risk-informed approach, we can go and check what ifs as well, right? So that's part of the risk assessments is, you know, if we get the foundation wrong, what does that look like, right? If we don't understand the strengths, so, you know, look at all these failures. What happens if we miss a foundation unit? What happens if we don't understand the shear strength of our tailings? What happens if our construction methods don't work, or the material we build a dam with changes material? So I think the whole point of this is, you know, the reason why tailings dams are so much more complicated is because, you know, when we build a water dam, we typically go at this water dam, we'll close off the river, we'll put a coffer dam, and we'll do all the construction in a single phase, typically. Nowadays, we're wanting more water and more flood mitigation. We're tending to raise those dams, and there's not a lot of experience in the water dam industry for doing that, because a lot of that work for construction hasn't been going on for a while. But, you know, in tailings dams, we regularly build a dam and then we keep adding to that dam year after year and decade after decade. So I think, you know, we want a system that allows us to identify what this dam needs to do in its performance and understand what we know and what we've assumed, and also understand what happens if these assumptions, and test these assumptions, particularly if we get them wrong. I think that's one of the things we need to be a little bit more humble about, our ability to find these weak layers, right? Places like Cadia, they did a lot of drilling and they didn't find it. People can say they should have found it, but, you know, we're gonna miss things all the time in these designs, and we need to understand what happened, what's the consequence of those, and that's why we want simple basic systems to do this and work that out. I don't think I've answered the problem, but I think future risks need to be anticipated in our designs.
Yeah, I think I could add to the question, and that is there are a number of hidden risks that people aren't fully aware of. Things like, and some of them are to do with people. So things like, you know, a consultant is typically commissioned to design the next raise. When they're commissioned to do that, they're not necessarily commissioned to look at what happened previously. They may not have been the designer previously. They're not always asked to look at, okay, what does this imply for closure? What's the next stage going to look like? What's the life of mine facility going to look like? So they're risks that can be somewhat hidden. Another major risk is the turnover in the industry among clients and among the companies, as well as among the consultants, so that corporate knowledge is lost. One of the things that I see when I review design reports is often there's a lack of commentary. You know, you'll have a table of parameters presented without a commentary on where they came from and how they might have changed over time. And I think that sort of information is vitally important. But the same can happen on site. They may be monitoring, they may even be monitoring in real time, but unless a commentary is written up and maintained, you don't learn from it. If you're not interrogating the data, you're not learning from it. And things like interrogating, if your critical slip surfaces pass through the foundation, just do a little exercise to help your certainty about it. Assess how much increase in strength would you need to force it out of the foundation, and then think about that strength. Is that feasible? And if it's close to being feasible, test for it. Don't just assume, okay, I'm going to accept. I've pressed the button. I've got a factor of safety. That's all I need. Interrogate the data that goes in and interrogate the results that you get out, and keep doing that and comment on it.
Well, and maybe as simple as, do I have a weak foundation unit? What does it cost? What does it cost to remove that weak foundation unit at the construction site, right? And is that and if we want to go and move to this just a LARP, that means sometimes if you have a weak foundation unit and you remove that you've eliminated that risk, right? And it's much better to eliminate the risk than design for it. Okay.
Yeah.
And that's one of the things we want to be reinforcing. So, it's false economy to leave these weaker units where we don't have the ability to test all of them. If it's really cheap to pull it out, and I mean not a almost negligible cost to the project, then we should be pulling them out because it's a simple thing to do. So you should be doing this high-end engineering if it's cheaper. If it's cheaper to dig the material out of the foundation than to do the engineering testing, then you should just dig it out of the foundation and eliminate that risk. And I think that if we do nothing but actually get people thinking about what's the right way to do this and where can we make these reasonably simple decisions and cost balances to reduce risk, I think that's going to help the industry out, because that I think the step change that governance has made to the management is this is what it does to the design.
Another example is dam break analysis, and while there's still a lot of confusion about that, it at least forces you to think about conceivable, credible failure modes, that sort of thing. It forces you to think about those things that in the past, when we didn't do dam break analysis, we may not have thought of. Sometimes we overthink it, but I think it's good. It's better to overthink than underthink.
Yeah.
Kathy?
Yeah. One last question for David. What do you think about the distinct ways different mining companies assess ALARP? Should there be more effort to achieve less vague criteria for this discussion?
Yeah. Look, I think the difficulty with ALARP is that it's a log plot of number of deaths along the horizontal axis. It's expressed in terms of a log plot. It's unfortunate it's become so quantitative. Number of deaths to a log scale on the horizontal axis and the frequency of that number on the vertical axis. In other words, it's something like the probability. And it's essentially an annual frequency as well, which is also a problem. You can define the number of deaths pretty precisely. So what you end up with is typically a series of dots that are vertical or in a range of numbers of deaths, population at risk, but with a range of frequencies. And you can have, the more you have on the panel trying to come up with the frequencies, the more range you'll get probably for frequencies. What you need to do, if you're going to lower the frequency to something that approaches ALARP, you must do something, not just lower it, or we think it should be this, but do something positive to physically lower it. So, for example, simple example, there was a U-shaped tailings facility. It had been closed for many years. It happened to have a low spot on the two sides of the U. On one side, it would report, if it spilled on one side, it would report to the coal preparation plant. On the other side, it was an exploration camp. Simply raise those two sections so that it can't spill there. It will spill at the bottom of the horseshoe where there's no population at risk. Things like that. If you can do something, then you've justified in lowering your frequency because you've actually done something. You might have changed the N as well. So, do something. So you're doing something to actually move the point to the bottom left-hand corner, which is what the aim is.
Thanks, David. Another question for Brett. Are there any plans to add consequence categories based on PLL?
Sorry, not at the moment. We're not changing the consequence categories in ANCOLD. We're trying to anchor off the current guidance, and we don't want to rewrite that guidance. So the answer is we're not planning to do that.
Yeah, I'm not sure this question, you can both answer. If we design tailings dams in the same way as water dams, for example, to full height with proper drainage and foundation treatment, monitoring and impermeable barrier, wouldn't that immediately remove a lot of risks issues discussed today? Cost will be higher, but still less than cost of dealing with the tailings failure.
Look, I think the days of just going and doing these upstream dams and minimizing cost and are not there. I don't think the industry understands the cost of doing this longer term. So my belief is when you actually look at these dams as a life cycle from the start to the finish, it's actually a lot cheaper to build these dams a lot more robustly, especially in mining. When you have mining operations that are upstream dams, and I've gone and I've gone to some dams and done some reviews last year and this year, and they're building an upstream dam, but every 30 seconds a truck drives past the dam with 300 tons of waste rock, right? And I asked them, why aren't you building this why aren't you just building this as a downstream dam? You're driving past the dam and you're dumping 4 kilometers down the road. It's actually costing you more money to move all this waste past the dam. Why aren't you just building this as an upstream dam? So I think we as a designing industry need to challenge ourselves, and it's not always that simple, right? But I'm just using it as an example that sometimes we think that reducing the volume of the dam embankments is cheaper on an economy scale, because some project guys got a metric of reducing the cost of the dam, and that the cost of the dam is all about unit rates. But we're spending $70 a cubic meter sometimes to build a dam, when if we built it bigger with mine waste, we could probably do it for $1.50 a cubic meter, right? Or even negative, because it's actually a shorter haul. So I think what we're trying to say is that let's just step back at the front end when we're looking at these new dams and say, what can we do to reduce the risks, and what does that look like? And sometimes they're very simple and sensible things that we can do. So, going and doing these really sharp, sexy looking designs that are razor blade thin aren't really what we want to do as an industry. We want to do something that's simple and robust and has a bit of degrees of freedom, because actually building these bigger things is usually cheaper for a miner who's geared up to move 300,000 tons a day, right?
And on that point too, I often ask operators, why are you doing it this way? And they said, but we've always done it this way. So when you think about how people lay out a mine, obviously they've got to put the pit where the ore is, but they typically locate the waste rock dumps starting from the point of egress out of the pit and then moving outwards from there, because they want to minimize haul, particularly in the short term. They'll put the processing plant close to the pit for the same reason, to minimize the haul for ore going to the process plant. And they'll put the tailings facility further away, because everyone knows that the cost of pumping a slurry is much cheaper than the cost of hauling rock, which it is by a factor that most people don't understand, but it's probably around 3 to 5 times cheaper, something like that. The trouble is, if you choose to build your dam, you need to build the dam out of something. If you choose to build the dam out of waste rock, for example, and you locate the dam a long way away from the pit, then your haul distance to the dam is going to be high. And the higher the dam goes, the more fuel you will need. So that becomes a major cost. So I think we need to go right back to that point and think about what is the best layout of our mine. The only thing that's certain is the ore body. Its location is fixed, obviously, but the rest of it we can play around with. And if we had a more whole of life plan, as Brett says, we look to minimize overall costs, but we do it by potentially using waste rock, dumped waste rock, to form a very robust dam behind which we can put the tailings, which may or may not be dewatered. It's all those things are still up for grabs.
Thank you. Thank you, David and Brett, for your informative presentations and valuable insight, and to all of you for participating. Thank you all. Over to you, Lindro.
Thank you, Kathy, David, and Brett, and also to all attendees, because I know that we exceeded the allotted time, but I didn't want to interrupt this very enriching discussion between the experts that was triggered by the questions of many attendees. So thank you. I would like to conclude the event then by acknowledging all listed here, starting with the ANCOLD Queensland Emerging Professionals Committee, especially to the state representatives Erin and Joel, to the ANCOLD Emerging Professionals National Convener Brandon, to ANCOLD Executive, to Lishman Associates, especially to Michelle for dealing with their registrations, for managing them, to the Queensland Tailings Group, led by Kathy. And I really want to thank David and Brett. They have been kind enough with me. They have to bear with me for about a year that took to organize this event. And I think that it was very well attended because of them. So thank you very much. And for all attendees, because of your attendance and questions, it made the presentations very interactive. Thank you very much. This concludes the event.
Thanks all.
Thank you.
Thank you.